So first, let's start with crystal systems, lattices and unit cells. A crystal is built up from regularly repeating structural motifs, and structural motifs could be a single atom, or it could be a molecule or group of molecules or atoms or even ions. This is one-dimensional repeating structural nodes. This is in 2 dimension, this is in 3 dimension. We'll understand what is unit cell. It is actually, the unit cell is an imaginary, please remember this this term, parallel piped, that contains one unit of the translationally repeating patterns. So translationally repeating pattern, this and also this word parallel pipe should be marked. What does that mean? So parallel pipe, it's derived from parallelogram with the 2 parallel sides. So obviously we should have parallel sides here. And what does this mean? Translationally repeating patterns. It means that if we move, let's say that we have identified this gray block as the unit cell. Now if we move translationally by 1 unit, that's the 1 unit, and it is completely indistinguishable from the block next to it. Similarly, we can move in the g directions and it is indistinguishable. Mathematically, we can express it in terms of r dash equals r and some integers, and these are the vectors a1, a2 and a3 in x, y and z directions. R dash is the translated point from r by integral multiple of a's, like this. So this is, let's say this is the unit A. So we translate it and they are indistinguishable. Let's understand it further with one more example, which is the diamond, very famous diamond crystal. So let's say this is a lattice of 3 by 3 unit cell, and we have identified one unit cell which, if you translate, it forms the translationally repeating pattern throughout the lattice. Whereas this one, if you consider this as the unit cell, you cannot perform this kind of translational motion and obtain the indistinguishable block in the adjacent blocks. So this is unit cell, and we can call this the component of unit cell but not unit cell, and this is the crystal lattice. Based on this definition, one is the translationally repeating unit, the other one is the parallel piped. We have 7 crystal systems. The different types of crystal systems depend on the angle and the length of their sides. We have cubic, where all 3 sides, all 3 A, B and C, length, breadth and height, they are equal, and also the angle is 90 degree, 90 degree, 90 degree. So similarly, we have tetragonal, we have orthorhombic, we have hexagonal, we have rhombohedral, we have monoclinic and triclinic. And we can also look at these structures in terms of basic symmetries. For example, the cubic has 4 C3 axes. What is C3 axis? If you connect this corner to that corner, we have C3 rotational axis. Similarly, tetragonal has at least one C4 axis. C4 axis is this one. It has a C4 axis. Or some, like monoclinic, can have only one C2 axis, like this, passing from this part to that part, and we can have hexagonal C6 axis here. These 7 crystal systems can be further divided into other small sub categories. So for example, the cubic systems, we have if there are the single element, we have the simple cubic. In simple cubic, only corners of the cube are occupied by the structural motifs. Atom, it could be atom or the molecule or ions or anything. So in simple cubic, we have 1 atom per unit cell. Why 1 atom? Because there are actually 8 atoms. We see 8 atoms in each corner, but these corners are shared between 8 different unit cells. So 8 divided by 1 by 8 is 1 atom per unit cell. Similarly, for body center, you have 1 inside, so 1 plus 1 is 2 atoms per unit cell. And for face center, we have 4 atoms per unit cell. And the examples are polonium, lithium, europium, and for FCC we have a lot of examples like gold, silver, nickel. Let's stick to the cubic system for some time now. So in cubic system we also have the mixed systems where we have like CCl type, like cesium chloride type of structure, where this is the cesium which occupies the body part of the cube, and the corners are occupied by chlorides. And in this case we have the coordination number 8. Similarly, in sodium chloride type we have face center structure, and here the coordination number is 6. In fact, there's a simple rule: if the radius of the cation divided by radius of the anion, R plus R minus ratio is 0.41 to 0.21, the coordination number expected is 4. Similarly, if it is 0.73 to 0.41, we expect the coordination number 6, and greater than 0.73, we expect 8. In fact, for cesium chloride type, this is consistent with this radius ratio rule. For example, cationic radius and anionic radius ratio is 0.93, and therefore if you look at this chart, it has coordination number 8, which is expected. Similarly, for sodium chloride, the radius ratio is 0.54, which is somewhere here, and we expect the coordination number 6. But we have to be careful because there are some exceptions. Lithium chloride, which has a 0.28, which is much lower. It should have coordination number 4, but it still has the sodium chloride type of structure. Similarly, rubidium chloride has a very high radius ratio, 0.82. We should expect a coordination number of 8, but again it has the sodium chloride type of structure with the coordination number 6. So there are other factors which affect the coordination number. Some of them are polarization effects of the anions, the nature of the bonding, so we have to take into consideration many other factors. But still, this rule is able to predict some of the ionic crystals like cesium chloride, sodium chloride, potassium chloride, and other things. If we are dealing with complicated mixed element crystals, it is desirable to understand the crystal in terms of coordination sites. For example, if there is a coordination site 4, we can imagine it as a tetrahedral site, and for 6 we can imagine an octahedral site like this, and for cubic with the coordination number 8 we can imagine cubic site like this. So I'll give one example. Sodium chloride type, sodium surrounded by 8 chlorides, or vice versa, you can have the chloride inside or sodium outside. So we can imagine this as the octahedral site like this, and with the 6 corners and 8 sides. 6 corners are occupied by chlorides, and one octahedral hole which is occupied by sodium. Similarly, we can imagine another structure is zinc blende, very common structure in cubic system. In zinc blende, examples are zinc sulfide, indium phosphide, and zinc selenide. We have this tetrahedral site, which is like zinc surrounded by 4 sulfur. 4 such tetrahedral sites per unit cell. This is really helpful when we are dealing with other structures. See, for example, this is a zinc blende with 4 tetrahedral sites arranged like this. But if we have copper iron sulfide, where we have copper sulfide and iron sulfide occupying the tetrahedral holes, you can see this red and blue. It is helpful if we understand the crystal structure in terms of tetrahedral and octahedral and cubic sites. It is easier for us to draw the polyhedral structures of the crystal. Similarly, for casterite we have copper, and then we have zinc or iron, and then we have tin and sulfur. Similarly, we can have stenite, you have copper, iron, and also the tin structure. And similarly, sodium sulfide, we have antifluoride structure. So we can imagine all these structures, different structures in terms of tetrahedral sites or octahedral site, and it's really helpful. Similarly, for calcium chloride type of structure, we can identify two sites. One is 8 coordinated cubic site, the other one is 4 coordinated tetrahedral site. The whole of the tetrahedral site is occupied by fluoride, and the whole of the cubic site is occupied by calcium. Similarly, we have another very famous crystal system, which is called spinel structure. In a spinel structure, for comparison, I have here a rock salt structure where you have the octahedral site. So we have in spinel structure, we have octahedral as well as tetrahedral sites. The octahedral sites are occupied by element A. The whole of this tetrahedral site is occupied by element B, and other things are these blue ones are oxygen. So we can easily identify the crystal structure based on this tetrahedral and octahedral and cubic sites. Similarly, I give one more example, very famous nowadays, the perovskites. Perovskite, you can write unit cell like this, but when you have to draw the more complicated structures, I think it's really interesting to draw in terms of polyhedra. In the perovskite, the 8 octahedra sites are connected like this, and the center position of these octahedra sites is occupied by the either calcium or cesium or some, even we have hybrid organic inorganic perovskites like this, where you have methyl ammonium ion in the center position. So similarly, we have more diverse structures like this. So it is really helpful to understand the crystal structure in terms of octahedra, tetrahedra, and cubic sites. Now I will briefly talk about the how we identify the crystallographic planes, and just discuss in brief the Miller indices. So Miller indices actually represent two things, very important. One is the crystal plane. The other one is the direction, very important. Both are important. It represents the planes and the direction. So when it represents the plane, this is the term, this kind of bracket is used, HKL, sorry, this is HKL, and this kind of simple bracket is used when it represents the plane, and a family of plane is represented by this kind of bracket. And to represent the direction, we use square bracket like this, and to represent a family of directions, we use this kind of bracket. So let's understand what does that mean. Miller indices are the reciprocals of the intersection distance. So first, let's talk about the Miller indices, how they are used to represent the planes. For example, if this blue plane, and let's say this is the unit, this is y-axis, this is x-axis, this is g-axis, this plane is here, sorry, this blue plane is here, somewhere here, and this plane has only one intercept, and that is in which direction? Obviously this direction, in the y direction it has the plane intercept. So in the x direction it does not have the intercept, so it is infinity, and in the y direction it intercepts at this position, which is one unit, because b, the length of this part is b, so it's 1 unit. And in the g direction also it is not intercepting, so it is infinity. Similarly, for red plane, it is only intercepting in which direction? G direction. I mean, what is this direction? Yes, G direction. This is G direction. So this part is G direction. And similarly, for the green plane represented, we have only intercept in the x direction. But since we have this infinity term here, in Miller indices we represent the reciprocals of the intersection distances. So reciprocal of infinity is 0, infinity is 0, and 1 is 1. So this plane, the rate plane is 0, 0, 1. And similarly, blue plane is 0, because infinity, inverse of infinity is 0, 1, and 0. And for this green plane, we have 1, 0, 0. We can also have the negative bars in the plane. For example, we can this crystallographic axis. If you remember, in the beginning, we had the origin here. We imagine the crystallographic axis x, y, and z here as the origin. What we can do is we can move the axis. This is arbitrary. Crystallographic axes are arbitrary. We can move this origin here, and if we do that, the blue plane now becomes it has no intercept in the g direction, no intercept in the y direction, but it has some intercept in the y direction, but in the negative side, -1. So this plane can be represented at 0, 1 bar, and 0. Similarly, we have 0, 1 bar, 0, 1 bar, 0, 0. All these things can be identified, and all of them together is represented by this notation, which is the family of 1, 0, 0 plane. We can again look for other more complicated planes, like for example 0, 0, 2 or 0, 2, 0 or 2, 0, 0 plane. So suppose the plane is here somewhere. Let's imagine the red plane. So red plane has the intercept, no intercept in the x direction, no intercept in the x direction. There is no intercept, and it also has no intercept in the y direction. Y direction also no intercept, but it has actually some intercept in the g direction, but that intercept is exactly half of the length of this box. So half unit, we say it's a half unit. See, half unit. And if you again Miller indices, you have to, it's the reciprocal of the intercepts. So you have 0, 0 and 2 plane. Similarly 0, 2, 0 and 2, 0, 0 planes for this screen. Similarly, we can have 1, 1, 1 plane that has intercepts everywhere, x-axis, y-axis, and g-axis. So this is a Miller indices. And now again we can represent family of these planes. All right. So now how can we use the Miller indices for directions? For directions, let's understand how do we identify the direction of this plane. Connecting this part. So this is the plane that connects. This connects these points, these 4 points. So this is 1, 1, 1, 0 plane. It has intercept here. It has no intercept in this direction. By vector analysis, we know that resultant, the direction of the 1, 1, 0 plane would be here, this part. So this is the direction. I can show you in 2-dimensional. This is the unit A and unit vector B. So now if you have the vector 4A, how do we represent the 4 2 bar in 2 dimension? Now we have 4 units here, 1, 2, 3, 4. This is the origin. We go in the negative direction because it's minus 2b. Now to represent the direction of this this plane, 4 2 bar plane, we draw the diagonal. Please note this bracket. It's a square bracket. Similarly, we can find direction for different planes. 0, 0, 1 plane has this direction, 1, 0, 0 has this direction, and this is this corner to that corner is the 1, 1, 1 plane. And for 0, 1, 0, this is the direction. For 1, 1, 0, this represented by brown arrow is the direction. Even in the case of direction, we have family of directions. For example, 1, 0, 0, 0, 1, 0, all these planes are represented by this notation. After the Miller indices, let's understand the relationship between Miller indices and the interplanar distance. All right, so let's understand first the one-dimensional system. Let's just focus on this part. In one-dimensional system, if this is the unit A, marked by A, and let's say this is the plane, so I'm marking this as brown is this is the plane, so this plane, and there is another plane here. All right, so I'm talking about these two planes, but this is the unit. So this can also be a plane, but I'm taking this plane. So obviously this is the distance between the two planes, and it can also be written in terms of Miller indices, which is A divided by h. H is the component of this plane. So in that case, we have this relation: 1 by the d spacing square is equal to Miller indices square divided by the length of the one unit square. So we can extrapolate this idea for 2-dimensional system. In two-dimensional system, we have this distance between these two planes represented by Miller indices h and k in this fashion, exactly like this one. And similarly, for 3-dimension, we have this equation. So h square, k square, l square divided by a square. So this represents the distance between the two planes in 3-dimension, and it is very helpful. Now, if we know the type of planes, we can actually, for example, if it is a 1 1 1 plane, 1 1 and 1 plane, so obviously we have how much is the under root 3. So this is the relationship between d and lattice parameter and the d spacing for 1 1 1 plane. So this is 1 1 1 plane, 1 1 1 plane, 1 1 1 plane. So similarly, 1 0 0 plane, what would be the value? 1. Now these two are 0 0, so 0, and this is also 0. So in other words, we have this 1, whole thing is deleted. So this is equals to simply A for 1 0 0. This is the relationship between the d spacing and the side of the lattice parameter. So similarly, I suggest you find the relationship for other planes, much more complicated planes like 2 0 0 planes. What is the relation? And similarly 2 2 0 or things like that. So you can do it as an exercise. Similarly, we can also calculate trigonometrically. We can calculate d spacing, the relationship between the Miller indices and the d spacing for other crystal systems like tetragonal. For tetragonal, we have d, and this is the relationship. And again, we can do some exercise here also. We can find the relationship between distance between different planes and the Miller indices or the lattice parameter. Similarly, we have for orthorhombic, this is the relationship. Furthermore, for hexagonal also, we have the relationship between d spacing, lattice parameter, and the Miller indices. We also have for rhombohedral, it's more complicated, but still we have the relationship, and you can actually practice by using different planes like HKL, values of HKL. I think this is L, sorry, this is L. Similarly, we have for monoclinic and for triclinic. It's much more complicated, but these equations are very useful. So I have provided the relationship between d spacing, lattice parameter, and the Miller indices for all 7 types of crystal systems.